Hello, and welcome to lesson 25 of this Introduction to Calculus with Wolfram U. The topic for this lesson is the fundamental theorem of calculus. So let's begin with a brief overview of the lesson. So far in this course, we've talked about differential calculus and a bit of integral calculus. Now, originally, differential calculus arose in the problem of finding the tangent line to a curve, like you see over here, the sine curve, and you want the tangent line at a point, and that's what differential calculus tries to do. It tries to find the slope of that line at a point. Now, integral calculus, on the other hand, solves the problem of finding the area under the curve for a function. So if you look at the sine function, then it tries to find the area under this curve between the two limits over here. Now, what the fundamental theory of calculus does is it ties these two ideas together. And in this lesson, what we'll do is to go over this very important theorem. In fact, by far, this is the most basic fact of calculus which you really should know in order to apply it in practice. Okay, so let's begin with the idea of an integral function. So here I'm defining a function of x, which is given by the integral of t from 0 to x. So basically what it does is it takes the function g of t equal to t and integrates from 0 to x. Now obviously, if x is 0, then the value is 0 because you're integrating from 0 to 0, so you get back 0. And in general, it calculates the area under the curve from 0 to x. So that's the integral function f of x, and here is a graph of the function and x. And what you notice is that as x increases, the value of this function also increases because the upper limit over here increases. So the integral function is increasing because the area increases in this case as x increases. Now, the point is that there is actually an explicit formula for this integral function. So what we do is we begin with the integral from 0 to x and break it up into n parts, and then we set up the Riemann sum. So in this case, the Riemann sum is going to be g at xi star, the sample points, times the width of each subinterval, and then you sum them all up and take a limit, and what you get back is x squared over 2. But then you remind yourself that the antiderivative of g of t is also t squared over 2 plus some constant. So here's a check for that. So it looks like the integral function for g of t is actually an antiderivative of g of t. Now that looks very surprising. So what we do is we try and go a bit deeper and develop some intuition for why that might be the case. So let's begin over here with the integral function again and think of the difference at 2 points f of x plus h and f of x, two close by points with h being very small. Now that difference over here would just be the area of a tiny strip because h is very small. So here's a picture. The area of that strip is simply the width times the height, which is g of x. So the area is h times g of x, but then that is f of x plus h minus f of x. So if you divide, then you get back this relation over here, but as h goes to 0, that says that f prime of x is equal to g of x. In other words, f of x is an antiderivative of g of x. And it is this remarkable fact which is summarized in the fundamental theorem of calculus. Now there are two versions. That's version 1 over here, which says that if you have a continuous function g and you define f to be the integral from 0 to x, from a to x in this case, then what you get back is a function, integral function, and this integral function is actually an antiderivative of g. In other words, f prime x is equal to g of x. So let's try to understand that a bit more by looking at some examples. So let's say you'd have the function f of x given by the integral from 0 to x of sine of square root of 1 plus t square dt, and you integrate it, then you just get back sine of 1 square root of 1 plus x square. So here's a check, namely, if you take the derivative of an integral function, you will get back just the original function. So that's a summary over here, which says that if you take a function, you integrate it, and then you differentiate it, you get back the original function. Now, the problem is that the upper limit itself might depend on x in some complicated way. In that case, you must apply the chain rule. So let's say if g of x is the integral of 0 to x square of the same function, then if you differentiate that with respect to x, you will need to account for the x square, so you get back a factor of 2x over here. So let's check that, and you get back 2x times the sine of square root of 1 plus x raised to 4. Okay, so let's now go on to talking about why these integral functions are useful at all. So there is a function called the Fresnel function, which is really quite useful in optics and highway design. After all, when you design a highway or you design, let's say, a railway line, you need to worry about the turns, and that's where this Fresnel function comes in. It's an integral function of a sine function. So we have this in the Wolfram language. It's called Fresnel S. So that's Fresnel S and its derivative on the same plot. So the blue plot is the Fresnel function, and the orange plot is its derivative, which is just the sine function over here. Another very useful function is the error function, which is also an integral function, and that's used in statistics and probability. So here is the error function with its derivative. So you have the error function, which is blue over here, and the derivative, which is just the normal probability curve. And what happens is, as you approach very large values, the probability of everything being covered is almost 1. So that's why the values over here are almost 1. Okay, so now there is another more useful version of the fundamental theorem, and that's version 2, which says that suppose you have a function f and you find an antiderivative of that function by some means, then the value of the integral from a to b of this function f is the antiderivative at b minus the antiderivative at a. So in other words, the integral of an antiderivative can be found quite easily by simply working out the difference between the values at the upper and the lower limits. So that says that differentiation and integration are actually the inverse processes of each other. And that's quite a remarkable fact. So for example, if you're asked to find the integral of x squared from 1 to 4, then you first work out the antiderivative, which is x cubed over 3. Then you plug in the upper and lower limits. So you get 4 cubed over 3 minus 1 cubed over 3, and the answer is 21. And you can check that with integrate and get back just the same result. So that brings me to the end of this lesson. But the main point is that the fundamental theorem of calculus is one of the most important theorems in calculus, because it says that differentiation and integration are the inverse processes of each other. And in fact, its real utility is to compute integrals by using antiderivatives. So basically, using the antiderivatives is much easier than using Riemann sums. So instead of calculating Riemann sums, we would calculate antiderivatives. So the next lesson we'll talk about indefinite integrals, but before that, do review this lesson over here, because we've covered one of the most important theorems in calculus, and that's going to be used all the time. So let's stop over here. Thank you very much, and I hope you have learned a lot in this lesson.